Here we have a simply supported beam with a uniform distributed load of 500 newtons per meter acting along it, and an offset concentrated load, 5,000 newtons, that's 15 meters from the left end. And we're asked to find the deflection in the center where the beam is going to deflect something like this. It's a good chance the peak will be someplace over here between these two loads. So the process for finding this will be to take two cuts
and to develop the moment equations and to integrate them. M1 would be ax minus wx squared on 2, and we know that's equal to eiy double prime, and we can integrate that twice. And in the second domain, M2, we'll inherit all these first ones, ax minus wx squared on 2, minus p, this concentrated load, which I'll just call p, and the distance to it would be x minus 15. And again, we can integrate this twice. We'll have four constants, C1, C2, C3, and C4 that we'll have to chase down. And from there, we can start to work and solve this problem.
Thankfully, there's a better way. We can use deflection or beam tables, as they're called, where someone's already worked out the deflection equations for many different forms of loading. Here's an example of one. It's important to make sure you pick the right loading pattern. Here we have a cantilevered beam with a concentrated load acting at the end. It shows us what the elastic curve looks like and where Y max is located. This would be Y max. This would be the slope at the end, which would be out here. And this is the equation for the deflection if you wanted Y at some specific spot other than at the end. So if you wanted to know it right here. As we look down, we have a uniform distributed load acting on a cantilever. Here we have a bending moment applied to the end for a cantilever. Now we move into the simply supported beams. This one is a centrally acting concentrated load. Y max occurs at the center, and here's your deflection and your theta and your deflection at spots other than the center. Here is one for an offset concentrated load. That's the one we need today. That's one of our configurations. And we also have a load that is uniformly weighted as well. And the nice thing about these loads is that we can use superposition principle on them. And superposition says that we can add the loads, therefore we can add the deflections. If we look at our beam, and we know that it's going to deflect something like this, and we're looking for the deflection at the center, which we'll call Y total. Y total will be the Y due to the distributed load plus the Y due to the concentrated load. So let's start with the distributed load. If we look at the table entry, we have Y max occurring at the center, which is where we're interested in. So this equation right here will give us the deflection at that point. We're told EI is 2 times 10 to the 8, so we know the value for that. And I'm going to omit the negative signs. We generally know this is both acting down. Y for distributed load will be 5WL to the 4th on 384 EI, which is 5. Distributed load value is 500 newtons per meter. We have a length of 20 meters to the 4th, 384, and EI is 2 times 10 to the 8. And from there, if we adjust the units, we'll get 5.2 millimeters for that. Now let's find the deflection due to the concentrated load. And the table entry for concentrated loads that are not at the center looks like this, where we're going to be trying to find the deflection here at L on 2. And unfortunately, that's none of the entries in here. X max is not at the center, In our case, this would be 11.18, which is just a little bit past the center. And over here is the value for y at locations other than at the peak, and it's valid for x less than a. Now, for x equal to a, it's giving the value here as well, which could be useful. So from here we have y concentrated, PB on 6EIL x cubed minus L squared minus B squared x. So we'll get P is 5,000, B is 5 meters, 6 EI is 2 times 10 to the 8, L is 20, X is the location of interest for us, which will be 10 meters cubed, minus 20 squared minus 5 squared times 10. And from here we'll get 2.86 millimeters of deflection due to that load. And with that we have our answer. Y total will be 5.2 millimeters plus 2.86 millimeters for a grand total of 8.1 millimeters of deflection here at the very center. Let's take a look at a few more examples. Here we have a distributed load acting on a cantilevered beam with load reactions here at the wall of M and F, which we could calculate. And we're asked to find a deflection at the end here due to this concentrated load. If we take a look at the beam table for this, we see that the only entry we have is for a uniform load that reaches the entire way across. Well, part of the trick with working with these load tables is being able to modify them to use this table to define this type of load. Let's define the equivalent load as follows. Here's our beam now with the distributed load acting only out here at the end. And we can say that that would be equal to a beam that had the load acting the entire way across, which that is in our tables, plus a beam where the load acted upward over half of the length. So this downward acting load here plus the upward acting load here is equivalent to the original load. So that's a good starting point for us. Let's next show the Sag model for this, which would be the deflections greatly exaggerated. So here's what we're looking for. We're looking for this, which we'll call Y end. Here we have the load acting the entire way, so we'd have a very large deflection here, which I'll call Y1. And here the load acts up, and it'll curve as if it was a short beam of length L on 2. After that, there's no more load down here, so this portion of the beam will stick out perfectly straight. And as such, we can make a right triangle out of it. We'll call this height here Y2, and this one will be Y3, and there's some angle theta in here which we can find. And the length of this is L on 2 as well. Now, it's shown greatly exaggerated. The true amount of deflection will be very small, so this would still be relatively flat down here. We're just drawing this greatly exaggerated, which is what our Sag model does. Now to find this Y3 value, since these angles are so small, we can use the arc length formula, that L is equal to R theta. So in our case, Y3 would be L on 2 times theta. And this is useful when you have a load that doesn't travel the entire length of a beam for some reason. And that's why the tables include entries for finding theta. It allows us to do this. Let's use the tables now. We can say then, to solve for Y end, it will be Y1 minus y2 minus y3, where we're calling down positive here, right? Again, we tend to use the absolute value of the table entries. And let's solve these one at a time. So y1 will be WL to the fourth on 8EI. And y2, we can also use this formula, except we're going to apply it for L on 2. With that, we'll get W L on 2 to the fourth over 8EI, which will be WL to the fourth over 16 times 8EI. And for now, I'll just leave it like that. And then y3 will be L on 2 times theta. And theta, at the end of this beam right here, the angle, we can find here by again plugging in L on 2 as the length of that short beam. From here we'll get L on 2, W L on 2 cubed, for the length of the short beam, over 6EI, which will be WL to the fourth. 8 times 2 will give us 16 EI. And with that, we have all three of our values. So y then, and let me factor out a WL to the fourth on 8. It appears we have that in all of our terms. So WL to the fourth on 8 EI. And we'll get 1 minus a 16th minus 2 times 6, a 12th. And this will be 48. 48ths minus 3 48ths minus 4 48ths, which will be 41 48ths. And our final answer then will be 41 WL to the fourth on 384 EI, where this represents the total deflection at the end due to this type of loading. In fact, now that we've found that, we could make our own table entry. Here we have a beam loaded at L on 2, and we could say then it would be negative 41 WL to the fourth on 384 EI. And we could follow a similar process to find the value for theta. We would calculate theta here. We'd have a theta 1 and a theta 2. We can subtract the two of them to get theta at the end as well, and we could enter that. And if we use this type of a beam often in our work, it will be worth developing that table entry. Let's look at another interesting application. Here we have a cantilever beam with a concentrated load acting at the center at L on 2, and we have our beam table entry for a cantilevered beam where it's located at the very end. And we could modify that by treating the beam as a shorter beam of length L on 2, which we know will deflect like that. And we could enter L on 2 in here for that entry. And the remaining portion we would treat as sticking out straight with L on 2 and theta, and this y would then be L on 2 times theta, where theta will be calculated from this formula using L on 2 in here as well. We could find the total deflection y at the end as y1, this deflection here, plus y2. However, there's something much more useful that we can do with these deflection tables, and that's the case of indeterminate structures. If we add a support out here at B, this beam becomes indeterminate in that we have a moment, a force, and now a new force at B. in which case we have 3 unknowns and only 2 useful equations. Some of the forces in the x, there is no x forces here, so some of the forces in the y and some of the moments about any point, we can only handle up to 2 unknowns. And this has 3. So this beam is indeterminate. Let's look at how we can use beam tables to solve for an indeterminate beam. Let's separate the loads into an equivalent. So we have our beam with a centrally acting load plus a load B acting out here at the end, where this would be L, and this is L on 2, L on 2. And our deflection curve, we know, looks like this. It'll curve down to here. We'll call that Y1. And then from here, it will stick out straight. And that makes a right triangle. Well, the length of this is L on 2. We could calculate theta, and Y2 here will be L on 2 times theta. And for this beam, we just have a load pushing up, and we can use our load table here, whether it's going up or down, and that will be the value for that deflection. So this will deflect up like that. Call that Y3. And here's an interesting case. At x equal to L, y is equal to 0, we have no appreciable deflection here. So this becomes a boundary condition, which lets us say then that y1 plus y2 has to equal y3. There's no deflection at B. And again, we can use the deflection table equations to generate this. So y1 will be P L on 2 cubed over 3EI. Where here we're treating this as a short beam and we're just bending it down. And that reduces to PL cubed 32 EI. We can calculate Y2 as L on 2 times theta, which would be L on 2 times, now over here is our value for theta, P L on 2 squared over 2EI, and that will reduce to P L cubed over 16EI. And lastly, Y3. Now here we can use the formula directly. The force is B, and this would be L cubed on 3EI. So we can quickly generate the 3 equations for deflection, and now we can plug them into here to solve for this. So we'll get PL cubed on 32EI plus PL cubed on 16EI equals BL cubed on 3EI, which basically says that the deflection down has to equal the deflection up for this loading up here. We can multiply through by EI, and notice that these drop out. So the solution is independent of EI. This solution will be valid for any cross-section of material I and for any material that we picked. We could pick a very soft aluminum, or we could pick a fairly rigid hardened steel. We're still going to get the same answer. Also, we see that L drops out, so it's independent of the actual length itself. And from here, we get, if we do 2 and 2, we get 3/32 P is equal to B on 3. So B will therefore be 9/32 of P. What's truly fascinating here is that we did not have to do any moments. We did not have to sum any forces. We were able to solve for this end condition directly without ever knowing any of these back here. The elastic nature of this beam as we bend it tells us how much load we anticipate B taking up when it tries to support B. We're able to go directly from this load configuration to our equivalent loads, to our equations, and then solve for the force at B without ever going in and doing any of other moment or force equations, which is truly remarkable. Once we know this, that beam becomes determinate and we could finish it and find moments and the force at the wall after that. So an extremely useful benefit of these elastic curves. Here we have another beam with 3 supports, which makes it one redundant support. And notice that if we do sum of the forces in the y equal to 0, we have A plus B plus C is equal to L. And if we take some of the moments about, let's say, A, we'll get P times A equals B times B plus C times little c. And we have no way of developing a third useful equation. We have 3 unknowns and 2 independent equations. We could try some of the forces in the x equal to 0, but there are no x forces, so that one's wasted. And you could try some of the moments about B or some of the moments about C, but they'll just generate redundant equations that are similar versions to what's up here. They won't take us to a solution. What we need is an alternative set of equations to generate our third equations. The Sag model for this is going to look something like this. And notice right here, y is equal to 0. We have a nice constraint here. So a better way to think about this problem would be to think of support B as a second force acting inside this system. With that, we can make an equivalent system where we have A and C with a load P acting on it a distance A away, plus a second system where this is A and this is C with a load B acting up at a distance of B away. And note that the deflection here at a distance B is equal to y1. In this Sag model, we have a y2. Since the deflection at B is 0, y1 has to equal y2. And we'll find that this will generate our third equation. So we have 1, 2, 3 independent equations, and we can solve for all 3 unknowns. Here's the beam table entry, but be careful when computing this. The A, B, and C of our problem don't correspond to the general A, B, and C that are in the table. We have to modify those, so be careful with those substitutions. And also note that this equation here, which is the one we need to use, is only valid for x less than A. We're looking for the deflection here due to P. And that does not fit this criteria. And that is not at all uncommon. And there's a fix for that. We need to flip it around so that this is B and this is A. And here's our load P acting a distance of A in. And we need a deflection out here, which will be y1, and that's a distance of B from this end, which will be C minus B from here, and that's how we modify our beam to find y1. When we're trying to find y2, which would be the beam bending up out here, the table will work fine in this case. In fact, we're at x equal to A, where A is B in our case, and we can use this form right here directly instead of the longer form. And those two equations will allow us to solve for the support reactions A, B, and C as a function of P. So if you have time, give that a try, and thanks for watching.